Section 8.8 deals with applications of Taylor polynomials. So you've learned what a Taylor series is, and of course you've seen, um, well, you've learned what a Taylor series is, and Taylor series can be used to approximate integrals. Okay, and you've seen that already. That they can be used to approximate integrals, definite integrals, and Taylor polynomials are the same as Taylor series. It's just, what if if you didn't take all the terms of a Taylor series? What if you took 4 terms of a Taylor series or 3 terms of a Taylor series? Well, what you would have then is a Taylor polynomial. And when you have a Taylor polynomial, you can also ask the question if you have an approximation, how accurate is the approximation, which is valuable. So let me give you a moment to copy this example down. Okay. All right. So, all right. Before we get to this, let me point one thing out. One thing. I want to go into WebAssign real quick, just to point something out here. Um, One moment. Okay, so what I did was thought about this a little bit. How many are finding the Section 8.7 exercises do take some time to do? How many are noticing that with the series problems, the Taylor-Maclaurin series, Section 8.7? How many are noticing? Yes, yes. Okay. Wow, a lot of thumbs up on that. Okay, so what I've done is I've changed the due date for the Section 8.7 exercises. Originally, the first batch of exercises was going to be due tomorrow, Saturday, but I've decided to make it due on Sunday. And then the second batch of exercises from 8.7 will be due Monday. So that'll give you a little more time to finish up your exam and then maybe finish get the 8.7 exercises done on time. How many find that helpful, that adjustment? Great, great. Thank you, everyone. All right, that's great, And there's so many thumbs up, I can't remember all the names, but thank you, everybody. All right, great. My goal is for you to be successful. So now, naturally, of course, that first, because we're limited on days, I have to have the first batch of 8.7 exercises due the same day as your exam is. But naturally, if you need to finish your exam, then use the extension on those 8.7 exercises. Okay, great. Well, I'm happy about that. I just kind of had a feeling, and I'm happy that that this is helping you out. Okay, so now we want to approximate the cube root of x by a second degree Taylor polynomial. Okay, second degree Taylor polynomial at a equals 8. And then we're asking a question that we haven't asked before. How accurate is this approximation? Now, of course, if you have an alternating series, then you can find out how many terms you need to get to a certain level of accuracy by the alternating series estimation theorem. But if you don't have an alternating series, how are you going to answer? How are you going to determine accuracy? So there's a theorem called, and I'll go to called Taylor's inequality. Taylor's inequality is a theorem that can help us answer this question. And it works a lot like the exercises you had in section, like in section 5.9 for your approximate integration formulas, Simpson's rule, midpoint rule, trapezoidal rule. You had error-bound formulas. So this is also an error-bound formula. And in the numerical integration error-bound formulas, you had to find that big K value, which was dependent on usually, like for trapezoidal midpoint rule, it was dependent on the second derivative. Well, Taylor's inequality works very similarly. Hold on here, I'm trying to get this. Let me blow this up a little bit more here. Okay, you have here an error bound. So R sub n is the remainder. It's the difference between the function evaluated at x and your nth degree Taylor polynomial evaluated at x. The difference in those values is less than or equal to this right-hand side. And it's no problem well, I'm going to show you how to get those values, but the m value has to be greater than or equal to the m plus first derivative over x minus a less than or equal to d, or the absolute value. Okay, so I'll show you how this works. But let me ask you this: why are we doing a second degree Taylor polynomial around a equals 8? Why are we picking a equals 8? Why aren't we picking a equals 10 or something like that? Why choose a equals 8? Intuitively, why are they picking that value? That's right, Robin. It's a perfect cube root. So you'll notice in all of these Taylor expansion problems, they're always expanding around a value of a that can be easily computed when you compute derivatives. So, okay, let's get the second degree Taylor polynomial. So second degree Taylor polynomial means you're going out to, that means the polynomial is a second degree. So the highest power is an x squared. So when we look at the solution, okay, of course, I'm going to build up this polynomial. I can't use the tables are of no help here because they don't have the cube root of x in the tables, right? And so, all right. So, all right, the function is x to the third. F of 8 is 2. The first derivative is 1/3 times x to the negative 2/3. F prime of 8 will equal 12. And then finally, the second derivative is computed as you see. And the second derivative evaluated at 8 is negative 2 over 288. Okay, I'll give you a moment to copy that down. So what you do now is you construct your second degree Taylor polynomial. And we call it T sub 2. T is for Taylor. 2, the sub 2 there is for the degree of the polynomial. So now that we know the values of the derivatives about a equals 8, we just apply the Taylor series formula, but only with the first 3 terms. We stop there. We stop there because it's a second degree Taylor polynomial. And so you get your T2 of x. You get your second degree Taylor polynomial. Let me give you a moment to catch up here. Okay, are there any questions so far on this? Of course, you know, we're going to simplify our coefficients here. We have to simplify the coefficients. Okay. Thank you. All right. So now what we're going to do is we're going to use this, we can use this Taylor polynomial to approximate values. Like we can approximate the cube root of 8.1 or 7.9. We can use the Taylor polynomial to approximate cube roots that are near the cube root of 8. But that'll make, but let me just say, are there any, I want to move on to the, now to the applying the Taylor inequality. Are there any questions up to here? Are we good? WebAssign for section 8.8 will want you to, for most of the time, to type in the answers. But these are not, you know, you can type these in. That's not a problem. Okay, well then let's move on. So how accurate is this approximation? What are we doing with this second degree Taylor polynomial? We're using it to approximate the cube root of x. Okay, the cube root of 8, we don't need a Taylor polynomial. The cube root of 8 is 2. But if we want the cube root of 8.1, what we would do is we would let x be 8.1 and we would plug it in. We put 8.1 in for x, and we would compute that on the right. We would compute the value using the Taylor polynomial. And that's fine, but we want to know how accurate would the approximation be. If you're interested in cube roots of values between 7 and 9, how good is this second degree Taylor polynomial? How good is it? And, you know, depending on how, well, we need to know, okay? We need to know. Because, of course, if the accuracy wasn't good enough, we might want to go out to a third degree Taylor polynomial or a fourth degree Taylor polynomial. So we're going to use Taylor's inequality here. And we're getting a bound on the error, or the remainder, which is the difference between the Taylor polynomial and the cube root of x. So we have here the formula. We have the right-hand side. This is your error bound on the right-hand side. And in the Taylor formula, and that's also in the book, but oddly enough, the formula is in section 8.7 in the book. It's not in section 8.8. But once again, I will be sure to share that formula sheet with you. Okay, and you'll have it in the recording for now. So n plus 1 factorial is 2 plus 1 factorial because n is 2. Okay, and then the n plus first power here is going to be 3. And a equals 8. So all I'm doing, I'll come back to this. I'll come back to this. All I'm doing, again, is here's the right-hand side. Here's the error bound, right? And I computed n plus 1 factorial. N plus 1 I can get because n is 2. And now a was equal to 8. So that's how I get what I had here. But there are two more things I need to find. Two more things I need to find here. I need to find the m value. Have to find that. and I need to put in something for x. I need to put in something for x. And we want to be as conservative as possible. We want our error bound to be, we want the bound on the error to be essentially as large as it can be, because that way we're being the most conservative. We don't want to say the error bound is small when it isn't small. So this is why the m has to be greater than or equal to the absolute value of the third derivative over the interval 7 to 9. So the third derivative is the n plus first derivative. Well, n is 2, so the third derivative is 3. So now you have to compute the third derivative. You have to compute the third derivative. Okay, which isn't hard. So what I did was I took the derivative of the second derivative. Okay, that's how I got this. So like in the video, if you go back and you'll see the second derivative, I took the derivative of that, of the function, and got this. All right, so far, are there any questions up to here? Okay. Well, so now we need to find out where the third derivative is maximized over the interval from 7 to 9. Okay, so that's what we need to do. And it works similarly to those error-bound formulas that you had in section 5.9, the approximate integration. So I want to see, first of all, if this third derivative is increasing or decreasing over my range of x. So what I do, of course, it's the absolute value of the third derivative that I'm interested in. But because x from 7 to 9, those x values are positive, the absolute value of the third derivative here will just be the same as the third derivative. Okay, so we can take care of that little technical matter easily. And what do I need to know about this third derivative? What key thing do I need to know about that third derivative in order to find out what m is going to be, that m value? What's the key question regarding the third derivative? What do we want to know about that function, that third derivative, over the interval from 7 to 9? Is it blank or blank? Well, we know it's going to be positive, Josiah. We know it's going to be positive because the x to the 8 thirds, if we are between 7 and 9 on x, it's going to be positive. But well, and okay, but how? That's good, Robin. But how are we going to know that? How are we going to know that? Let me just, okay, good participation. We're on the right track. We're on our way here. In or DEC. What are the keywords I'm looking for here? In or what? INC blank or DEC blank. What are the keywords? So this is like Wheel of Fortune. We have to fill in the what's missing. I hate to just give you the answer. There we go. That's right, Robin. Is that derivative, that third derivative there, very good. Is that third derivative increasing or decreasing over the interval from 7 to 9? Well, the x to the 8/3 in the denominator, do you think the third derivative is increasing or decreasing with x? What do your instincts tell you? Is this third derivative increasing or decreasing with x? What happens to x to the 8/3 power as x gets large? Does the x to the 8/3 grow or get smaller? If you graph x to the 8/3 on your calculator, let x to the 8/3, okay, John, hold that thought. X to the 8/3, if you graph x to the 8/3 on your calculator, does that function increase or decrease? Just plot it on your calculator real quick. Does x to the 8/3, is that function increasing with x or decreasing with x? That's right, Tyreek. Very good. It's increasing. Okay, well then, if that's increasing, what can you tell me then about 1 over x to the 8/3? That would have to be decreasing, right? Because if you have 1 over an increasing function, 1 over x to the 8/3 would be decreasing. So this tells you that over the interval from 7 to 9, our third derivative decreases with x. So now what would the value of m be? What would the value of m be? We have to put in a value for x. We have to put in a number there. Some number from 7 to 9. So if the third derivative decreases with x, okay, think of a, you know, I mean, I'm just drawing a little picture here. You have a decreasing function. It's obviously not drawn to scale. 7 to 9. Okay. What value are we going to put in for x? The 7 or the 9? What value makes the third derivative, the absolute value of it, the largest? The 7 or the 9? I can give you the answer, but I'd sure love an answer. The third derivative decreases with x. It decreases with x. So is the third derivative maximized at x equals 7 or x equals 9? That's right, John, x equals 7. So therefore, our value of m is going to be 10/27 times 1 over 7 to the 8/3 power. Right? That's what it has to be, and that's what you pick. So that's what you're going to take your m value to be. Okay, now we have that. Now we have our m value. We have almost everything taken care of. We have the m, we have the 3 factorial there, we have the 3rd power. The last part is the x minus a. Okay. The x minus a is this part. But a equals 8. A equals 8, right? Okay. Give you a moment to copy that. I'll be right. One moment. Just to kind of, I'll come back, but I want to talk about this real quick. This, this 1 that's here. So if we go back to the formula, and I'll come back here. Go back to that formula. We have this x minus a. And we want that to be as large also as possible, because we want to maximize the bound on the error so that we're being very conservative. Well, the absolute value of x minus 8 is your absolute value of x minus a. So since x is between 7 or 9, the largest that could ever be is 1. Remember, we pick an x value in the range there to put in, and x minus 8 would at most would be equal to 1, because it 7 minus 8 is negative 1, 9 minus 8 is positive 1, but the absolute value of that is 1. And so now you have your error bound. You have it. And in WebAssign, remember, it's very you have to have a very accurate answer. So you don't want to be like approximating things like 7 to the negative 8/3 ahead of time. You want to, you notice I carry all this stuff out, all these values out, and then later I approximate. So the error bound meaning that the bound on the error in approximating the cube root of x between x values from 7 to 9 using that 2nd degree Taylor polynomial is 0.00035. So that means if x is between 7 and 9, the approximation the 2nd degree Taylor polynomial T2 of x will be will approximate the cube root of x within 0.0035. Okay. Are there any questions on that? Any questions at all? So it's not bad. It's not bad. I mean, now, if you needed more accuracy, then you would need to take more terms in the polynomial to get more accuracy. But you see, that's an important question. Maybe, you know, even in today's world, right? If you need a certain level of accuracy, how many terms do you need to take? It could be a billion terms, right? You don't know. And the more terms you take, the more computing time it takes. So it's an important question, always to see how, you know, how accurate your approximation is. And what I've done here, this is just actually from the book here. But what I've done is in this figure, or what the book's done, the author's done, is he's drawn the cube root of x here, and he's drawn the Taylor polynomial. And you can see that the Taylor polynomial here, okay, does a very good job. I mean, here by the way is 8, right here. Let me see, it goes 3, 6. I'm looking at the notches. It goes to 15, so that's 3, 6, 9, 12. So this is 8 right here. And the polynomial does a very good job. The second degree Taylor polynomial does a very good job of approximating the cube root of x over, you know, this range from 7 to 9. Does a very good job. I mean, look how I mean, you can barely distinguish between the two curves. Okay. All right, are there any questions on that? All right, so let me make one more comment then. I'd like to go to the next page and finish out here, but are we good on this? Are we good? Okay, so I need just a couple minutes. What I want to do is I want to show you how to apply the polynomial approximation, the second degree Taylor polynomial approximation. So, like, let's say you wanted to approximate the cube root of 8.24. Okay, maybe you're on a desert island and you want to approximate the cube root of 8.24, and you don't have a calculator, right? How are you going to do that? Well, you've taken calculus 2, so you can get the second degree Taylor polynomial. So the cube root of 8.24 would be approximately the second, that would be approximately the same as evaluating the second degree Taylor polynomial at x equals 8.24. Okay. And you notice 8.24 falls between 7 and 9. I want the approximation to be good, so I got to stick between 7 and 9. So all you do is you plug in 8.24. You plug in the 8.24 for x, right? Because x equals 8.24. And you plug it in the polynomial. You're evaluating the polynomial at x equals 8.24. And then when you work out the math, you're going to get 2.0198. All right. And you notice all the math is easy to do. It's easy to compute polynomial values. All easy to do. You could do it on a desert island, right? Who thinks they could do this on a desert island? If they were not that I want you to be on a desert island, but say it would help you get rescued, you know. What was that movie, Castaway, where Tom Hanks had to compute calculations? Okay, Francesca knows what I'm talking about. Absolutely. Maxim, absolutely, for sure. Excellent. So now the cube root of 8.24, and notice we haven't touched a TI-84 calculator. The cube root of 8.24 is approximately 2.0198. But if you were to use the calculator, and just type in the cube root of 8.24, which would be 8.24 to the third power, you'd get 2.019803.268. So our approximation is very good. It's very good indeed. Okay, and that's an example of using a Taylor polynomial approximation. That's a section 8.8 example. And of course, we'll continue 8.8 on Monday. But are there any questions at all? Okay. And I'll just show you real quick. On the next page, what I did was I actually did do the calculations by hand that were needed to figure out the value of that polynomial. So you can, when you look at it, you can pause the video and look, but it's not hard. And all right, are there any questions at all? Okay, well, very good then. Very good class today. Thank you, everyone. Very good class participation. I'm going to stop the recording.